Welcome back to the lab. Our PFC module for the UPS is about to get real. Well, it'll get simulated at least. Making hardware takes a lot of time, okay? I want to make sure that when we do build this system, everything works great. So let's hedge our bet by assembling the circuit in our favorite circuit simulation tool, LTspice. If you aren't sure why I could ever possibly need a 2400 watt power supply that outputs 425 volts, check out our playlist on the larger project. For now, here's a glimpse of the architecture diagram for this module. We aren't simulating the digital or control parts of the design, only the power electronics. We'll be approximating the function of our control electronics with programmable voltage sources. Like I alluded to before, circuit simulation is a powerful tool. Simulation is a great way to uncover many issues with a design before hardware is in hand and it's too late to make a change. Simulation can actually save a lot of headaches. We recently discussed the power input filter and many other parts of our PFC power module. What I aim to simulate today is, well, all of it, together. I want to run a simulation that will show the peak voltages, currents, ringing. I want to see everything about how this PFC and H converter are going to work together, how they're going to integrate. And I want a way to verify that our efficiency calculations were correct. I want to make sure that we won't send transistors flying off the PCB. Detailed simulations containing many parts that are running in real time, like a transient simulation, they're notoriously difficult to run. They can take hours or days to complete, and these simulations sometimes crash because numbers get too large or it tries to divide by zero. Those glitches are called convergence issues. And when trying to put so many pieces together into one simulation and run it for this long, I had to pull some pretty crazy moves to make all the simulation models play nicely together. To give you a sense of scale, this is how large the simulation is. There are 2 full power supplies contained in the simulation, and that is not on accident. I'm not designing the PFC in a vacuum, nor am I designing the full H in a vacuum. These power supplies are meant to be used together. These are designed to be used as a pair and share that input-output capacitance on the DC link between them. I need to make sure that the combined ripple current of these two won't be too excessive. What you can see on this page is the result of multiple hours of work. 3 custom magnetic components are all designed and present. A lot of careful part selection needed to happen, and we optimized the passive networks that are responsible for controlling gate drive of our MOSFETs. There is a lot going on here, and I want to do it all justice, so let's just start stepping through the different pieces of the simulation one step at a time. There are 2 phases in the primary boost converter, which is the heart of our PFC. Thankfully, the analysis is somewhat shared between these 2 phases, since ideally, currents and voltages are equal in both, they're just time shifted and overlapped. Make sense? Yeah? I've highlighted one of those MOSFETs, U12, and I'm also showing the current through L4. This converter is operating exactly how we'd expect a buck to run. Current flowing during the on time flows through the FET, and this current shifts over to the diode during the off time. There isn't anything particularly special about how this boost converter is operating, except for the fact that we're working with mains on the input, so voltages get a little higher, component selection is more critical, but our controller is definitely the secret sauce. It's the most unique part of the switch mode power supply, since it can both gracefully handle the input voltage dropping to 0 volts once every couple milliseconds, and also modulates duty cycle proportionally. Also worth noting, I'm simulating the gate drive IC with an ideal voltage source, and this is a strong assumption, but it makes things run a little smoother. These voltage sources can source infinite current, but I think that's okay. And I think that's okay because the gate drive networks limit the peak current able to be sourced in and out of the MOSFET gates, so we don't really need to limit that here. I'm seeing a peak current of 2.4 amps when charging the gate and 5 amps when discharging, so that won't be too difficult to achieve with a gate drive IC. We just need to make sure it can handle that full 5 amps. The current sense filter you see now seems to work pretty well. This year's resistance allows for true differential signaling, which will likely reduce noise due to ground shift significantly. It has a pretty short time constant, but based on what I'm seeing in the simulation, it still appears very capable of filtering out the switching noise out of that current sense signal without adding excessive distortion. Feeding this current sense signal into a truly differential current sense amplifier will remove a lot of error due to a phenomenon known as ground shift or common mode coupling. Common mode coupling occurs when 2 signals share the same return conductor, or when 2 signals share the same ground. In this case, that current that we're talking about is the peak current of 30 amps through the MOSFET U12, and that can cause a small voltage to be present at the ground location near the circuit. That's not a problem for the MOSFET or for anything else, but it is for the current sense signal, since the signal is only 10 millivolts. A small ground shift could lead to a large error in the measured current. I don't have any concerns with the stresses applied to these components, and the efficiency looks reasonable. So I think we're ready to hook up the controller in the schematic. How exciting is that? So exciting. Of course, before we can finish up this design, I need to make sure that the stresses present on our output capacitors and the H converter are reasonable too. In this case, that's looking pretty good, at least for the capacitors. The 7 microfarad DC link capacitors are showing a peak current of 12 amps. Calculating the root mean square, or DC equivalent current, which is what you can use for power dissipation, shows 2.8 amps. That means that we have a lot of margin on the 7 amp ripple current rating for these caps. The what will hopefully be electrolytic capacitor, or C19, is also important, and these caps are, well, pretty sensitive to ripple current. In this case, the ripple current is just under 2.5 amps. For a capacitor this big, around a millifarad, a fairly standard electrolytic capacitor of this size should be able to handle that current. Shifting gears just a little bit, I would like to talk about the full H converter too. This converter is responsible for establishing isolation and taking a bit of ripple out of the PFC. We have 20 volts of voltage ripple as the holdup and the small part of the main cycle happens, and that's a bit too much for me to see on the DC link. I would rather not see that show up on the inverter output, so let's just crush it. One of the most frustrating design challenges that we faced while designing the power supply was part selection. Finding a MOSFET that met our requirements, was easy to drive efficiently, and didn't turn on too quickly was a real challenge. Normally, switching as fast as possible is important, but when we're talking about switching 400 volts as fast as possible, the rate of voltage change becomes extreme. The specification we can start to run into is called the maximum slew rate, or the maximum rate that the drain to source voltage should increase. That's why we implemented an incredibly slow gate drive network along with a supplementary external capacitor. Breaking the linearity of this timeline a bit, we eventually found that the 200 ohms we're about to talk about was too large of a gate drive resistor, so that came down to around 25. Regardless, let's still talk about the simulation as it was. The 200 ohm gate drive resistor that you can see along with the 600 ohm ferrite bead will crush this issue nicely. Those FETs will not turn on too fast anymore, but this quickly becomes a compromise between how much power we consume while switching and how much margin we have with the voltage slew rate specification. Not exactly ideal, but changing the voltage too quickly on the drain pin of a MOSFET can cause it to turn on. If the low side FET turns on because the high side FET turns on too quickly, that will be really bad. Exceeding the maximum change in voltage per time, or DVDT rating in our application, means that the FETs will shoot through regardless of if our gate drive signals are correct. That is not good. To leave nothing unexplained, shoot through is when both of our transistors are on at the same time, which dumps an incredible quantity of current and power into the transistors. That most likely leads to a short flash followed by a loud bang. Another issue that we wrestled with while designing this power supply came from ringing across the output rectifier diodes. In fact, this ringing causes the simulation to show voltage peaks up to 600 volts. This large voltage puts our diode at risk of being damaged, despite having 150 volts of design margin with the nominal voltages. What? This was so difficult to fight that I added 8 snubbers to squash the issue. 8! There's barely even 8 nodes. That's every single node has a snubber. Thankfully, switching from a standard rectifier to silicon carbide rectifier diode was exactly the push this design needed to bring the performance to an acceptable level. Well, that and adding a 10 picofarad capacitor from every node of the circuit to ground, that helped a lot too. This is modeling the random stray capacitance that occurs in any real circuit, just due to physical proximity, and this happens due to the fact that traces run near one another on a PCB. I'm really happy with how the voltage across the rectifiers look now. I'll be slow to remove any of these snubbers, really, despite how great this waveform's looking now with the straight capacitance modeled. That's because our assumption is currently that there'll be 10 picofarads of straight capacitance from every node to ground. If some of these nodes don't quite have 10 picofarads, perhaps some of that ringing will return to our circuit, and the snubbers will become critical once more. I'd rather have the pads on the PCB and not need them than the other way around. What we've just done, analyze some of the minute details of exactly how power will flow through the PFC, the H-bridge FETs, and rectifier diodes, but there is still more pieces to this circuit. The output inductor. This inductor is the final piece of the puzzle, the last required component between AC wall power and the DC bus. We targeted 400 microhenries, but 429.1 turned out to be a more convenient value. This inductor is, you guessed it, both hand-wound and custom. Apparently, 429.1 microhenries is not a standard component value for off-the-shelf parts. Weird, right? We designed this inductor to handle the full 2400 watts, and well, that's its job. It's not an easy job, but this is the component responsible for translating that 425 volt square wave into a 350 volt DC output. It needs to achieve reasonable voltage ripple performance while holding back 75 volts. That's not an easy task, but this is one of the few parts of this power supply that didn't cause me much grief. It just kind of worked. We've talked about inductor design before, and I don't have enough time to cover all of that information again today, so check out this video if you want to learn more about our design process for custom inductors like this one. You may be thinking that I skipped over a lot of steps or neglected some details, but well, in my opinion, that's really all there is to it. Obviously, a lot of work happened behind the scenes. There's an art and science to selecting appropriate components for an application. There isn't necessarily one right technology or one right component value for each of these circuits. The specific type of power supply being created, the switching frequency, and a couple other factors may lead an engineer to select one particular component value or component over another, but every application is different. There are hundreds of pitfalls that need to be considered. It may seem like this design, simulation, and all just popped into existence, but there was a lot of analysis that pushed this design to where you see it now. Thankfully, the analysis wasn't particularly different than any other switching power supply, so we didn't need to relearn a whole lot. All we had to do was apply the same analysis to an application with larger numbers. Despite how much we've accomplished, there's still a lot that needs to happen to translate this design into a functioning circuit board. Of course, I can't just stop here. I wouldn't be myself if we didn't zoom in on one key performance metric for this power supply. I need to verify that the efficiency of this converter is above 80% before moving on to the next part of this design. If we aren't seeing an appropriate efficiency, that means that I'm losing power somewhere I don't expect to be, and I'll want to figure out where. Maybe some parts of the design need to get tweaked. Remember, our target efficiency is above 90, so anything above 90 is great, but 80% is acceptable. There is 2400 watts coming out of this converter. This means that we can collectively dissipate 480 watts inside the UPS before there is a problem. It's not what I expected to see. The efficiency is plotted in teal, which is calculated as the ratio between output power and input power. That's hovering around 45%. It's about half of what we were hoping for and 25% less than we need. We're dissipating 1300 watts of power somewhere. Let's find it. There's a couple places that always come to my mind first, and that's the transistors. Let's make sure these are behaving. Shoot through or slow switching may cause these parts to burn a lot of power. That looks like around 18 watts right now. 18 watts in each of those transistors, so we found 40 watts. There's an additional 18 watts that we find being dissipated in the bridge rectifier diodes, the two that are actively moving current, so that's another 40 watts. The output diodes for the boost switch mode power supply are burning 9 watts for each phase, so wow, this is pretty punishing. I feel like I'm just getting nickeled and dimed, but that's another 18 watts gone. Man, maybe we're running out of watts. In the PFC alone, we've just found 98 watts of power dissipated. Wow. Translation, we're going to need one heck of a heatsink. This means that the PFC cannot be more than 96% efficient, but that's not so bad. We still got some power to work with. So I'll inspect the input filter just to make sure that everything looks reasonable here. Whoa. I think we might be onto something. We just found another 100 watts of power dissipation. The biggest issue seems to come from the stubborn inrush current limiter. We're modeling that as a 0.1 ohm series resistance, which leads to 70 watts of power dissipation. That doesn't feel quite right. Maybe this resistor value is too big, maybe we're not modeling it accurately. The biggest problem that I see comes from the fact that 10 milliohms of resistance translates into 7 watts of power dissipation. Wow, that is a lot. Our traces will need to be big. They will need to be pretty wide unless we want to make a space heater. Between the 4 inductors, fuse, and everything else, there's 105 watts of power lost in the input EMI filter. I'd say that it looks like our filter needs some refinement, to say the least. That's a great point for improvement, but there is more to this story. 1100 watts more. We haven't even scratched the surface. We haven't even found half of the total power that's being lost. So I plotted the power dissipated in all of our custom magnetic components and summed the result. The simulation is only reporting 13 watts in all of the magnetics. Alright? Another thing that comes to mind are snubbers. We did add quite a few, and this allows them to share the burden and allow for cheaper components to be used. Wow, actually there's a lot more snubbers than I realized. There's 10 snubber resistors on this PFC module. I guess that means that we learned our lesson from the previous phase of this project. I may very well never forget to add a snubber again. I might be adding redundant snubbers instead of forgetting snubbers. At any rate, the total power burned in these snubber resistors is 15 watts, with the most power-hungry one of these weighing in at 2.3 watts. Basically, what the simulation is telling us is that we're losing 1300 watts, but it's not in the PFC, it's not in the magnetics, nor is it in the snubbers or the input power filter. I guess let's check out the H-converter silicon next. These silicon devices are building the H-bridge, and those 4 FETs and 4 diodes dissipate a total of 115 watts. I noticed that the biggest offender is the high side FETs, those switching losses. Man. And we had to slow down these transistors so much to avoid turning on the low side FETs with this gate driver. Perhaps I was a touch too conservative, and our design could be significantly improved by switching faster. The 2 high side switches account for 90 watts of that 115. Yeah, this converter can be very efficient when switched hard, but the harder our converter is switched, the faster these switches turn on, and that can cause other problems. We'll have to optimize this gate drive network a little bit, but for now, let's count this as it is. Slower turn on prevents a couple issues and it makes a couple issues worse, but dissipating this much power leads me to believe that we have not found the optimal operating point. I don't know if you're keeping score, but I certainly am, and we've only still found 346 watts. And we're running out of parts. Where is this power going? There is only one more place that I can think of. Either the power is here or the simulation is freaking out. Remember, we're talking about 754 watts of power that we're trying to find. Like, what? It should not be this hard to find 700 watts of power. For the most part, I have the capacitors modeled with discrete resistors so I can tell the difference between the capacitor charging and the resistive losses. I'll display the power dissipated in all of the parasitic resistances, or the ESR, of these caps. I actually forgot about our PFC current sense resistors too, so let's add those in now and just pretend I didn't forget those. Total power lost, 12 watts. This is getting ridiculous. Just to verify, I'm seeing 1.88 kilowatts out and 4.62 kilowatts in, but I can't find the difference in the power. I've summed the power dissipated in every component, and this power is simply not here. No, there's literally only one other place this can be. We must be charging the bulk caps on the PFC, but our time window is so short that it looks like a flat line. We can't see that the voltage is increasing. So let's plot the net current flowing into the bulk caps, and there we go. We can see that it's always positive, so there's always current coming into these capacitors. That means that we're charging them. The average power flowing into each of these bulk caps is 1.12 kilowatts each. Whoa. If we take this charging into account, there's 2.24 kilowatts being pumped into the bulk capacitance on our PFC, and 1.88 kilowatts is making it to the load. That means the total quantity of power that's either being stored or output is 4.12 kilowatts. Now, if we take that power that isn't being lost, what's either being stored or output, and the 4.12 kilowatts coming in, that 4.12 kilowatts, and now we compare that to the input power, considering what we're saving away in the bulk caps, it's easy to calculate that our efficiency is actually 89%. 89% efficiency, that's not too shabby. Looks like we just need to run this simulation for longer. If we do that, the bulk capacitance will reach steady state and the simulation will report efficiency correctly. To be clear, running the simulation for 1.1 milliseconds took an hour, so you'll have to use a bit of imagination. I'm confident that the electronics are working and we can build this circuit without catastrophic failure. Our deep dive into losses may have been a bit of a wild goose chase, but that's how things are sometimes. Overall, I'm pleased. The PFC module meets our requirements and almost achieves our goal of 90% efficiency. Through further optimization of the full H gate drive circuit, along with the input filter, I think that we can safely say that we'll get another 100 watts of power out of this design and push our efficiency a couple percent higher above that 90% threshold. There's still some loose ends to tie up, but I think that the PFC module is coming along nicely. I'll sort out the details on my own, but if you're excited to watch our next power supply module get designed, then consider subscribing to be notified of our future videos where we'll be discussing the battery module architecture and dig into some detailed design for our next power module. I think that power supplies are great, and if you agree, let me know by hitting the like button on this video, following us on Twitter, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EEforEveryone, and thank you for staying till the end. Bye!